Welcome back to another Spark Understudy Explainer. Today, we're brushing up on the absolute bedrock of scientific inquiry. We're going to hand you the ultimate toolkit for solving physical science problems. Seriously, whether you're setting up a complex lab experiment or just trying to wrap your head around the fundamental laws governing our universe, you have to know how to measure things. And honestly, even more importantly, you need to prove those measurements actually make sense. That is exactly what we're mastering today. Let's get into it.
So here is our roadmap for today. We're hitting 4 main stops: mastering experimental variables, measuring the physical world, systems of scientific units, and rounding it all out with the power of unit analysis. We've got a lot of ground to cover, so let's jump right in.
Kicking things off with Section 1, Mastering Experimental Variables, the absolute core of scientific inquiry. To really demystify any experiment, we first have to understand the specific items we're manipulating and observing. It all starts right here.
Now, before we start sorting them into different buckets, we need to lock down the core concept. What is a variable anyway? Well, it's simply anything in your experimental setup that has the capacity to shift, change, or vary. It's the whole reason an experiment is dynamic instead of just static. But, as you probably know, not all variables play the exact same role in our studies.
This brings us to the clear dichotomy between the two main players in any experiment. First up is the cause. That's our independent variable. This is the specific condition that we, as researchers, intentionally manipulate. Second is the effect, or the dependent variable. This is the outcome. It's what we're measuring or observing to see exactly how it responds to the tweaks we just made. It quite literally depends on the independent variable.
But hold on, what if something else in the room suddenly changes and completely messes up our measurements? Enter the third type, controlled variables. These are the unsung heroes that actually establish that cause and effect relationship because we keep them totally constant. If we don't strictly control the factors we aren't testing, they're going to corrupt our results and completely ruin that vital connection.
Okay, let's test this out with a really concrete, everyday analogy just to make sure it's locked in. Imagine you're standing at a sink and you turn the tap's knob to change how fast the water is flowing out. Just think about it for a quick second. What exactly are the variables in play here?
Breaking it down, we actually see the scientific method happening right there in your kitchen. The rotation of that knob, that's what we independently change, right? We decide how far to twist it. The flow rate of the water is what we dependently measure. It's reacting to our twist. And crucially, the physical size of the tap and the overall water pressure in your pipes, those have to be our controlled baselines. Think about it. If the city randomly cranks up the water pressure while you're turning the knob, your entire experiment is totally invalidated.
Which brings us to the golden rule of experimentation, pulled straight from our source material. To keep your results completely valid, a researcher must change only one independent variable at a time, period. I mean, if you turn the knob and somehow swap out the pipe size at the exact same moment, you'll have absolutely no idea which action actually caused the water flow to change. Keep it strictly to one variable.
Moving on to Section 2, measuring the physical world, from variables to quantities. We know what we're looking at, but now we actually need to quantify it.
To be truly useful in physical science, a variable has to translate into a physical quantity. By strict definition, that means it's something that can be practically measured. We aren't dealing with subjective feelings here, we are dealing with measurable, hard reality. We're talking about the length of a desk, the mass of our rock, or the exact time it takes for an object to drop.
Now, what is really fascinating here is the strict hierarchy of these physical quantities. On one side, we have fundamental quantities. These stand entirely alone. They are completely independent of one another. Think of them as the primary colors of physics, like mass, length, and time. You just can't break them down any further. On the flip side, we have derived quantities. These are built entirely by combining those fundamental pieces. Complex concepts like work, power, and energy, they don't just exist on their own. They're derived directly from how mass, length, and time interact with each other.
And that perfectly tees up Section 3, Systems of Scientific Units, our standard of measurement. To communicate these physical quantities globally, scientists rely on universally accepted reference standards. Why? Because a number without a standard unit is, well, it's completely meaningless.
Take a look at these foundational fundamental quantities alongside their standardized SI units. This right here is the true international language of science. Whether you're in Tokyo, London, or New York, if you're doing science, you are measuring mass strictly in kilograms, length in meters, time in seconds, temperature in Kelvin, and electric current in amperes. It's this exact uniformity that makes global scientific collaboration even possible.
And just like derived quantities are built from fundamental ones, their units are built the exact same way. It's not magic. Area isn't some brand new mysterious unit. It's just length times breadth, or meters times meters, giving us square meters. Density? That's just mass divided by volume, giving us kilograms per cubic meter. The math literally dictates the unit.
Welcome to our fourth and final section, the power of unit analysis, proving the math. We've arrived at the ultimate tool for verifying that all our scientific building blocks actually fit together. This is where the rubber meets the road, and we find out if our brilliant ideas hold up to mathematical reality. I like to call unit analysis our mathematical truth serum. It is exactly how we check the accuracy of any physical equation. We do this by ensuring the units on the left-hand side perfectly match the units on the right-hand side. Look, if you're calculating velocity and the math on the other side of the equal sign leaves you with kilograms instead of meters per second, you instantly know your equation is fundamentally broken. Your experiment is going to fail no matter how pretty the numbers look.
Let's actually walk through checking the accuracy of a classic equation step by step. V equals u plus at. So final velocity equals initial velocity plus acceleration times time. Step 1. The unit for final velocity on the left is meters per second. Simple enough. Step 2. On the right side, initial velocity u is also meters per second. But what about at? Well, acceleration is meters per second squared, and time is seconds. When you multiply them, one of those seconds cancels out, leaving you with, boom, meters per second. Step 3. Compare both sides. Meters per second equals meters per second plus meters per second. The units perfectly align. It just goes to show that science isn't magic, it's a perfectly balanced equation from the ground up.
Which leaves us with one final provocative thought to wrap up our Spark Study Explainer today. If you can't measure a variable, define its physical quantity, or perfectly balance its units in an equation, are you really doing science at all? The physical world demands incredible precision, and hopefully you now have the foundational tools to demand that precision right back. Keep questioning, keep measuring, and we'll see you in the next explainer.